Welcome back. Hopefully you had a chance to do this exercise yourself, and hopefully it was easy and successful. And just in case, let's go over the details and make sure that we're all on the same page with this. So if we're going to prove something like this, here's what a complete and correct solution would look like. And there are some variations on this, but you need to have these basic components. So we're going to need a base case. It is a great idea if you write out what your method you're using when you start a proof. I'm going to use induction. So I'll write by induction. That reminds me that I'm going to use induction, so I better have two parts, the base case and the inductive hypothesis. It also clues in the grader or the reader if you're sharing your answer with a friend, which you're totally allowed to do in this class, except during exams. But on homework, we can totally share solutions. So if you put what you're doing, that really helps to clue your friends into how you solve this problem. So we're going to do the base case. Base case is usually given to you in the problem. Here I've sort of written the problem in a fairly poor way. I need to prove this, let's say, for all n greater than or equal to 1. Okay, now I've given you what the base case is. I've told you I want you to prove this for n at least 1. So I know that's my base case. So all I have to do is plug in n equal 1 and verify that it's true. We did this last time, but let's just do it. I like to write down left-hand side 1. Okay, I like to really indicate what I'm doing here, and this is good shorthand that you're allowed to use in your solutions. Right-hand side, what's the right-hand side? Well, it's going to be 1 times 1 plus 1 divided by 2, which is equal to 1 times 2 divided by 2. Hopefully nobody actually has to work this out. They are the same, so we're done. Okay, now how does the induction work? So when we're doing induction, we get to assume something. We get to make a hypothesis. Okay, and what we're going to do is we are going to assume the statement for some value of n. So assume for some n that the statement is true. Now we don't know which n it's true for, but we know it's 1, right? What this is going to allow us to do is say, well, we know it's 1, therefore it'll be true for n plus 1, which is 2, and so on. But assume for some n that we don't know, and the n is at least 1, because that's where our induction starts. Suppose we have 1 plus 2 plus 3 plus n is actually equal to n times n plus 1 divided by 2. Okay, that's what we're assuming is true. We need to show, and I like to write this down, especially the first few times you do induction, it's a great idea to just write down what you must show. We must show the statement is true for n plus 1. Sometimes that's actually tricky to plug into the formula, but let's see what it comes out to here. The left-hand side is 1 plus 2 plus 3 plus blah, 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 plus, and now we blow right past n to n plus 1. That's what the left-hand side is when I plug in n plus 1 in place of n. Okay, that's the trickiest part of doing a proof like this for induction, is just getting your statements right. So it's a good idea to take the extra time to write them down. Here, again, instead of n, I need to write n plus 1 whenever I see n. So here, I'm assuming the property p of n. I need to prove it p of n plus 1. So here, I'm going to take n, and that's going to become n plus 1. And then n plus 1 becomes n plus 1 plus 1. No, you don't need to be this pedantic about it, but I'm going to be for right now. So this is what we need to show. So I'm going to simplify this for a second, and then on the next board, I'm going to show it's true. Okay, I don't like the strategy of putting a question mark above this, but if you say I must show, then you're not declaring it's true. You're saying you must show it's true. I'm going to point out here that this is something we can apply induction to. And what's this side over here? This is equal to n plus 1 times n plus 2 over 2. And yes, you could have just written that down first. Okay, but this is what we're trying to prove. Okay, we need to show this, and we get to assume this bit that's in green. Okay, so I'm going to start with the left-hand side, and I'm going to deduce the right-hand side. Usually there's an easier way to add in. So here I can see my inductive hypothesis inside of the statement I'm evaluating, and that's going to tell me start here and then just hope that you get this. If you're careful with the algebra, it will all fall out. Okay, but start with the place where you can actually see what you've done. You can see what the change is. Okay, so I need to show this statement. So I'm just going to start by writing down the left-hand side. 1 plus 2 plus 3 plus n plus 1. Now, again, I've written this down in a very suggestive way, which is common to do during induction. So I'm going to evaluate this, and I'm going to say how I'm going to change it. So this equals, and I'm going to use green to emphasize that I'm using my inductive hypothesis. If you're doing a proof by induction and you never use this inductive hypothesis, you probably did the proof wrong, or you didn't need to do it by induction. So one of those is the case. So here I'm going to change the left-hand side to the right-hand side. So this is equal to n plus 1 divided by 2. That's what the green part is equal to. And I still have this black part, plus n plus 1. Okay? Now I've used my inductive hypothesis. The rest is going to be algebra. What I do is I sort of look at where I'm going. Okay, where am I going? I need a common denominator of 2. Okay, that's probably all I have to tell myself in order to get this to work out right. Look at what you want and say, okay, how do I take a step to get there? Just go one step in the direction and you'll usually end up in the right place. You don't have to think too far ahead with this one. So I need a common denominator over here. That's fine. So I'll leave the left-hand side the way that it, or this left part here, the way that it is, and I'm going to get a common denominator over here. Okay, now I need to combine my fraction. Luckily, I have a common denominator. That was the whole point. Here, notice I have n plus 1 and n plus 1, so that's going to simplify. I'm going to take more steps than necessary just to beat this and make the point. So here I've just combined them because they do have a common denominator. And now I'm going to notice n plus 1 times n, 2 times n plus 1. I can just combine that, and I get n plus 2 times n plus 1 divided by 2. I've just factored out my n plus 1 from the top. And now that's actually exactly what I wanted to prove. And now I'm done. Again, what have I done here? How does the principle of mathematical induction work? Well, what I did is I proved this is true for n equals 1. I proved it's true. And now I use my step function, my must show here. If it's true for n equals 1, then it's true for 2, because I can add 1. Think about my number line here. 3, 4, 5, 6. I proved it's true for 1 with the base case. And I said, if it's true for a number, then it's true for the next number. Therefore, it's true for 2. And now I'm going to reuse my inductive case. If it's true for 2, then it's true for 3. If it's true for 3, then it's true for 4, and so on and so forth, and all the way down. So I've proved this statement for all n by mathematical induction.